So now we will discuss first briefly the concept of Dirac's Bray and Kate notation, because it will be easier for us to understand the properties of linear algebra, some linear algebra for quantum computation. The discussion will be easier once we understand this concept. The writing will be easier for you. So, Dirac's Bray and Kate notation, it is a very compact mathematical symbol. This corresponds to mathematical symbol which is used in quantum mechanics and quantum computation. They are basically used to represent a quantum state. This Kate notation represents a quantum state, and this Bray notation represents the Hermitian conjugate of the quantum state. So, you all know that in case of quantum mechanics, the basic variable we use in quantum mechanics is the wave function psi. So, now in quantum computation, the notation Kate psi, you will read this symbol as Kate psi, psi Kate or Kate psi. It represents a Kate which corresponds to a column vector that represents the state of the quantum system. So, as I said, you all know already the quantum state of a system can have n number of linearly independent components, where n can take any integer values. So, all those linearly independent components will be represented as elements of a column matrix. So, corresponding to n linear components, n linearly independent components, we will have a column matrix of dimension 1 by n. So, n elements, having n elements, psi 1, psi 2 to psi n. And what about Bray notation? This is the notation for Bray. So, this Bray sign notation, it represents a Bray which corresponds to the Hermitian conjugate. Hermitian conjugate, what do you mean by Hermitian conjugate? Hermitian conjugate means, you remember I already used the notation psi star. So, complex, we are taking the complex conjugate of psi in quantum mechanics. But here we are dealing with a number of linearly independent components. So, complex conjugate of each of the elements we will take, as well as after taking the complex conjugate of each of these elements, we will take the transpose of this matrix. So, Hermitian conjugate represents actually complex conjugate transpose. What do we mean by transpose? I think you already know, you discussed in your matrix class. So, transpose of a matrix represents all the row elements will be replaced by column elements, and column elements will be replaced by row elements. So, here we have a single column. If we take transpose of this matrix, we will get a single row. So, Bray psi will represent this row matrix. Kate psi represents a column matrix having elements psi 1, psi 2 to psi n, and Bray psi will represent a row matrix having elements psi 1 star, psi 2 star to psi n star, where this star, psi 1 star represents complex conjugate of psi 1. You already know complex conjugate means if say psi 1 is A plus I B, then psi 1 star will be A minus IB. So, this is complex conjugate. The imaginary part, the sign of the imaginary part is changed. So, these complex conjugates will make the element of the row matrix in case of Bray psi. Now, a very important concept both for linear algebra and for the properties of Bray and Kate notation is the inner product. So, to understand inner product, let us discuss about dot product of two vectors. I have already considered two vectors in my last lecture. So, A vector, which is represented as A1 I cap plus A2 j cap plus A3 k cap. And let me consider another vector B vector as B1 I cap plus B2 j cap plus B3 k cap. Now if we take the dot product of these two vectors, I don't know whether you know about dot product or not. If you don't know, then just understand dot product means dot product of two vector will be a scalar quantity. And what will be the value of that scalar quantity? It will not have any direction because I cap dot I cap is 1. J cap dot j cap is again 1 and k cap dot k cap is again 1. If two vectors have same direction, their dot product will be simply the multiplication of their magnitude. So here A vector dot V vector will be A1 B1. Now what about I cap dot j cap? Remember, this I cap is the unit vector along x axis and j cap is the unit vector along y axis, and this x axis and y axis are mutually perpendicular. So x component and y components are linearly independent. They don't depend on each other at all. So in case of two linearly independent vectors like I cap and j cap, unit vectors along x axis and y axis, this I cap dot j cap will be 0. Actually, this dot product represent the component of one vector along the direction of the other vector. So suppose this is our A vector. A vector dot I cap represents the component of A vector along x axis, that means this value, and A vector dot j cap, it represents the component of A vector along y axis, and you already know that the component of A vector along x axis is nothing but A1. So A vector dot I cap will generate A1 only. If you take the whole vector and consider dot product of I cap of this whole vector with I cap, then I cap dot I cap will be 1, but j cap dot I cap will be 0 and k cap dot I cap will also be 0. The dot product of linearly independent vectors are 0 because these A1 have no component along y axis. Also A2 does not have any component along x axis. So these things represents some kind of projection actually. So A cap dot I cap, A vector dot I cap represents projection of this vector A along the direction of I cap. Now let me come to the case of A vector dot B vector. A vector dot B vector will be given by A1 multiplied by B1. There will be nothing like A1 B2 because I cap dot j cap is 0. Similarly, I cap dot k cap is also 0, so A1 B3 will not be there. Simply we will have A1 B1 plus A2 B2 plus A3 B3. So this is the dot product of two vectors. Now how can we express this dot product in the language of linear algebra? So in the language of linear algebra, this dot product is represented as, is known as inner product. And how we represent inner product? Suppose we have two state vectors, phi and psi. We have two state vectors. So how the inner product, the symbol for inner product will be like this, bra phi, and with the same line we write ket psi. Then bra phi is written as a row matrix phi 1 star, phi 2 star to phi n star, and ket psi is represented by psi 1, psi 2 to psi n. Okay. So when we multiply this row matrix with this column matrix, what we will have? this matrix has the rank of 1 by n, and this matrix has the rank of n by 1. This is a n by 1 matrix. So when we multiply a 1 by n matrix with n by 1 matrix, we will get a 1 by 1 matrix. What is a 1 by 1 matrix? 1 by 1 matrix is nothing but a scalar number. And what is the value of that scalar number? It is phi 1 star psi 1 plus phi 2 star psi 2 plus phi n star psi n. So only the similar components are multiplied. The same thing that we observed in case of scalar product. Only the similar components are multiplied while we take the dot product. So this inner product corresponds to the case of dot product in vector, and this is the symbol. So this is how we represent inner product in Bray and Kate notation. Next is the concept of outer product. So outer product is just the opposite thing. Here we multiply Bray with psi. In outer product, first we will write the Kate operator and then we will write the psi operator. So this represents the outer product. So how it will be? If we multiply a column matrix with a row matrix. So this is a matrix having the rank n by 1 and this is the matrix having the rank 1 by n. When we multiply, what will happen? We will get a matrix of the order of rank n by n. What will be that matrix? So what will we have? Psi 1 phi 1 star. Psi 1 phi 1 star. That will be the first element. No second element because we don't have any column here. Next, psi 2 phi 2 star. That is the second element of the first row. And the last element will be psi n phi n star. So the last element will be psi n phi n star. Psi 1 phi n star. Similarly, second row will be psi 2 phi 1 star, psi 2 phi 2 star. Last element is psi 2 phi n star. And that in the last line, the last element will be psi n phi n star. So you see the outer product results in a matrix. But what does it physically mean? So actually, when we multiply a Kate state with its Hermitian conjugate bra, when we take a outer product of these two, we will get a matrix. So this matrix actually represents an operator. When we apply this matrix on certain state, we will get some new result which will give the eigenvalues of this matrix. So that is the case. Actually this outer product represents an operator formed by these two matrices. And how do we discussed about normalization condition in quantum mechanics. What is normalization condition? So normalization condition represents that the total probability of finding a particle in the whole space is 1. So in a 3-dimensional space, we wrote the normalization condition as psi star psi dx dy dz is equal to 1. So this was our normalization condition written in quantum mechanics. Now how can we write it in terms of Bray and Kate? So in terms of Bray and Kate, the psi star psi thing I already discussed, it can be expressed in terms of inner product. So psi star psi can be written as multiplication of Bray psi with Kate psi. So this inner product of psi with psi should be equal to 1. This corresponds to the normalization condition expressed in terms of Bray and Kate notation. And orthogonality, that means linear independence of two states. Orthogonality means linear independence of two states phi and psi. I already told if two states are linearly independent, say I cap and j cap. If two vectors are linearly independent, then their dot product is 0. Similarly, if two states are orthogonal or linearly independent, then their inner product will be equal to 0. So these are the properties obeyed by Bray and Kate vectors. So remember, So what do we have for the properties of Bra and Kate vectors in short? So basically we have some 6 properties. First, you have to tell in Bra and Kate notation what is Kate psi. So Kate psi is nothing but a quantum state represented by a column matrix in linear algebra. So this is the first point you should say while discussing about the properties of Bra and Kate notation. What about the second point? So second point you will represent the Bra state, Bra notation. So it will be represented by a row matrix having complex conjugate of the components of these state vectors. So we have psi 1 star, psi 2 star, psi n star. So this is the row matrix represented by Bra psi. This is the second point. The third point involves the inner product. That means the scalar product of two vectors or two states. In quantum computation we will write about two states. So that is nothing but, I already told, multiplication of this phi 1 star, phi 2 star, phi n star with the column matrix psi 1, psi 2, psi n, and it will be given by a scalar quantity phi 1 star psi 1, phi 2 star psi 2 plus phi n star psi n. So this is the third point. The fourth point involves outer product. Outer product is represented by Kate phi Bra psi. First we will write Kate, next Bra. So I already wrote here the column matrix is multiplied with the row matrix. So here we have phi 1, phi 2, phi n, and for the row we have psi 1 star, psi 2 star, then psi n star, and their multiplication will be a n by n matrix. Only the first element and the last element I am writing. So the first element is phi 1 psi 1 star and the last element is phi n psi n star. So this is an n by n matrix which represents an operator. That is the fourth point. Fifth point is the normalization condition, which tells that inner product of psi with psi is 1, and sixth is the orthogonality condition, orthogonal condition. So if two states are orthogonal, if two states phi and psi are orthogonal, then phi and psi will be equal to 0. So these are the 6 points in short. So see, when in your exam, if you are asked to write about the properties of Bra and Kate vectors, Kate notations, you have to write these 6 points. Okay? Also you must explain that phi and psi are mutually orthogonal. This is the normalization condition. You have to write that. This is outer product, this is inner product, this is Bra notation, this is Kate notation, that you have to write. I have written in very short. And these same 6 points you can write in case of linear algebra in quantum computation. In linear algebra, a quantum state is represented by a column matrix. You will write like this. Then its Hermitian conjugate is represented by a row matrix. You will write this notation. The inner product is defined by this term. The outer product is defined like this. Outer product represents an operator, that line you should write, and the normalization condition is represented by this equation and orthogonality condition is represented by this equation. So these are the properties of Bra and Kate notation as well as the properties of linear algebra in quantum computation. So, in both the cases similar things you have to write. So, in this way we discussed about the two topics in our notes, that is linear algebra in quantum computation as well as properties of Bra and Ket notation.